invitation to the organizers, and thanks to you for staying until the end of the day in spite of the heat. So indeed, I will tell you about mean field games, how we used it to model dense crowds, and why we had to use this framework. But first, I don't know, though there was already a course on pedestrians, I don't know how familiar you are with the field. So I wanted just to remind you why do we study crowds, why are we interested in it. So what we usually think is about designing a building. So there are a bit two fields. Will the building be efficient for normal usage? And then you have some questions about emergency. But actually, there is a big market, I could say, about virtual crowds. How do you simulate crowds in video games, in movies, or you could imagine participative democracy if you want people to be embedded in a certain setting. So the systems I will consider are systems where we have transport and where we have to share space. So we saw it already. Exclusion will impose that there are some interactions between people. And this is all the more true that with pedestrians, we are in low-dimensional systems. When you are in 1D or in 2D, it's very likely that you will meet the other people, while if you are a bird in 3D, then it's more unlikely. And so the models are less focused on collision avoidance, but rather on alignment, on these kind of things. In low dimensions, avoiding collisions is really the issue. And in these systems, so they are out of equilibrium. We have fluxes, and we have also jamming transitions. So there are some characteristics of pedestrians. Some have already been mentioned. But basically, we have mass conservation. Okay, we don't disappear. But as we are in contact with the floor, we don't have momentum conservation as for a fluid. And this means that we are less constrained than a fluid. So as I said, it's in 2D space. And each pedestrian also can have a different destination. Though in most cases, we consider crowds which share something in common. The common being the destination. You can have 2 or 3 of them, but it's rare that you consider people going in any direction. And as Bertrand already mentioned it, these systems are not very inertial. We can do basically almost whatever we want. And so it means that we don't have so much physical load that will constrain our motion. And we need experiments to see how, in fact, we do behave. So, yeah, I just recall that to navigate, we have the choice of the angle of navigation and also the modulus of the speed that we use. Okay. When we are about modeling the system, we have a choice to look at it from the agent-based point of view or a fluid-like description. So what I will present today is more on the macroscopic side, though it's related to the micro. An important thing in crowds is about the density. So usually the first models were more designed for low densities, and I would say low means less than 2 pedestrians per square meter. But of course, there are a lot of issues and challenges for high density crowds. And so people try now to go towards higher densities. And so it's in this global evolution of the field that our work takes place. So in 2000, I don't remember the year, it must be 2018, we performed some experiments. So it was an idea of Alexandre Nicolas, who is now a researcher in Lyon. The idea was to perform with a crowd an experiment which is quite classical for granular matter. You take a probe and you deform the medium, and you look at the deformation around the probe. So here the probe was one of our students, which was in a cylinder, and we had volunteers to form a static crowd, and we had some limits so that we could vary the density of the crowd, and we had this cylinder going through, and we made a lot of recordings like this. So people were wearing some hats. Oh, it was 2017 already. I forgot. They had some hats with a tag to allow for the tracking. We could vary the density. So we chose 3 densities such that for the lowest one, people were not touching each other. And 6 people per square meter. Then it's like in the subway when there is a strike, so you are in physical contact. So the cylinder was always the same, but we also changed the orientation of people. They were most of the time facing the cylinder, but they could also have a random orientation. And we made replicas. We can, from the tag on the hat, we can detect the displacements. So here I have the cylinder and the displacements of the people around. And here is, so I will show you what we obtained, but also what we were expecting from the knowledge that we have with granular matter. So from imagine you have your kitchen table with crumbs. If you push with your fingers, the crumbs will accumulate in front of your finger. So that's what you see if you do simulations. Here it's a simulation by Antoine Seguin where we have adjusted the parameters so that we are supposedly in the same regime. And you see that grains accumulate in front of the cylinder. In contrast with what is observed in the experiment, what we found is that the density is on the sides. We have a wake behind, so this we expect. But we have also some void region, or at least region with low density in front of the cylinder. So this is quite different. We can also look at the displacement field. So for the granular matter, it's passive, so it will move only when it's pushed, and so it will be displaced in the direction of motion of the cylinder. Actually, I will show you, before going further, an experiment. So this is an experiment on granular matter. Again, it's a probe that you push, and you see that the grains are pushed in front of the cylinder, and there is a recirculation like a butterfly shape. So here on the left, we don't see the full butterfly, but there is a recirculation. And you see, or maybe you don't see, but I can tell you that for the pedestrians, we don't have this. The motion is not aligned with the forces that they would get if the cylinder was pushing. So people just step aside, wait, they are pressed together, and they come back. So it's a really different motion. And it's something that requires more ingredient than just being passive particles. So here I'm showing, so the density fields you see here are a bit different from the other ones. You must realize that to reconstruct the density field, we have to choose a method. And depending on the method, the density fields can be they can look differently. But what is common is that you have the highest density on the sides. And what was surprising is that you get this at relatively low density and also at high density, while in the meantime, you have introduced physical contacts. So it was not obvious that we would get the same. And I will speak about the random orientation later, but now we are so concentrating on the on people facing the intruder.
The symmetry of the response is not the same, or it's just it's a bit more closer to the intruder between brains and people? If you compare your response, is it that one is dipolar and the other one is quadrupolar?
Well, one is, it's quite different. What do you mean?
If you look at the velocity,
the velocity field.
When you expand it in spherical harmonic, for instance, can we describe it like that?
Okay, I'm not sure now. Okay. But yeah, we can discuss this. I thought I had added another figure, but it doesn't come out. Okay, just trust me that for the displacement, it's the same for all densities. We get this lateral displacement. So now that we have seen that these people are not grains, can we describe them with the classical agent-based models? So you have heard this morning about the social force model. You write the laws of mechanics as if you had real forces. It's only that these forces, in fact, are not real forces. They are just social forces that you think will represent the interactions. So Bertrand already said that this model has the problem to have too much inertia. I don't know if I have, yes. So what you will write in this model is that the acceleration will be equal to a sum of forces. So there can be a driving force to your goal, there can be interaction forces, and so on. So first, you have inertia. That's what Bertrand said this morning, but there is another important issue with this model, which is this. So the way you combine interaction is by making a sum. If you look at the drawing on the right, if you have, so the blue person must avoid the red one, it will have a certain reaction. Now if you double the number of red pedestrians, you know from your experience that avoiding 2 or 1 when the 2 are aligned is about the same work. But with the force formalism, you will double the reaction. So you see already that there is something wrong about combining interactions in this way. But still, there was the belief that at high densities, it would work because then physical forces would become important. So that was the state of the art when we did this experiment. There is another family of models that arrived about 15, 20 years ago, which was, it's called velocity-based models. So the idea is that you will take all the velocities you can take, which are more or less aligned with your goal, and then you will suppress all the velocities that would give a collision in a few seconds, and you will choose among the remaining velocities the one that is the best for you, given a certain, okay, you have to define what means best. But so for example, here you see in purple a set of velocities, and then the neighbor, when it crosses, it suppresses some velocities. And then you see that you could remove more velocities if you had more neighbors with a risk of collision. So it's another way of combining interactions, which is much more physical than the sum. So this gave rise to a new family of models. Actually, these models, velocity-based models, were already invented at the beginning of the 20th century in another field. It was to move ships in harbors. but then it was a different field, and it was like rediscovered, and it was also rediscovered several times for robotics. So these ideas are around, but okay. Now they came into the pedestrian field. Okay, so now we tried to take a social force model to see if it can reproduce our experiment. So I must say it's one of the simplest version of the model, but with this combination of forces. And you see that it's more granular-like, and yes, it relies on forces, and so the density accumulates in front, and you have this pushing in front of the cylinder. So it doesn't work. So our colleague Alexandre Nicolas said, yes, but I have developed a new agent-based model, and I'm sure it will work. So it's a more developed model where, in particular, the pedestrian selects its velocity in order to minimize the time to collision. So, among other things, but the time to collision is in how much time do you expect a collision with others. So if you minimize, you want to minimize the cost based on the time to collision. So you want to maximize actually the time to collision so that it occurs far in the future and you will have time to react. So this is what the simulation gave. So you see it's better than the social force model. You have a small opening in front, though it's not completely symmetric. But unfortunately, for the velocity displacement, it's again, you see the arrows on top, so people are still flying away from the cylinder. So it doesn't work either. And so we were stuck with this. What we could consider, at least, is that even at very high densities, even with physical interactions, we still have some forces which are not physical, which are social. And they would require two things. First, that we are self-propelled. Okay, we are allowing to move in a direction which is not aligned with the forces. And it seems that we anticipate when we do this. So I will make a small, to put this into another perspective, I will make a certain number of general remarks before going back to the modeling part. So people in the pedestrian modeling have the habit to distinguish several levels of modeling. So the strategic level is, for example, I need to go to my work, and I have some flexibility on the departure time, but still I should not travel after 9 a.m., for example. And then you have the tactical level. So there I will decide, okay, I will take this street, cross this square, and take the stairs, and so on. So it gives, in practice, usually, this provides a desired velocity for along your path. And then you have the operational level, and what we call pedestrian models usually refer to this last operation. So the idea is to avoid collisions and to adapt your real trajectory to what is happening. And usually we consider that the tactical level and the operational level are separated, that we can do them first, find the desired velocity, and then avoid collisions. So let's take a room with two doors, and we have the blue guy who wants to escape. So the simplest thing and there are models relying on this, is to assume he will take the shortest path. So you have Hughes' model there are many versions based on this. Now, it may happen that there is a jam in front of the exit, which is the nearest. So here you would think, okay, maybe he would take the other exit. So maybe you have to consider that the other path is shorter, not in distance, but in time. And this is more control theory. So you optimize just for one person according to a state that you know, and you want to minimize the cost. So you have to decide what is your cost, and this will give you your desired velocity. But there can be more complicated situations. For example, there you could assume that the other ones will also start to move and probably take the exit which is closest to them. So what do you do? So there you have to start to think about the future. What will the others do in the future? So you may decide to take the other exit, okay? And you have even more complicated situations. Here you have two groups, which one will go where, and so the decision can be quite tricky, especially that you have to foresee what others will do, and themselves they will have some strategy. So it seems very difficult, but so what we usually assume to be able to do something is that the others will optimize the same cost. That is, if I was at their place, I would do what they will do. It's a hypothesis. But if you don't have this hypothesis, it's tough.
So it's assumed that the red, so if I'm a guy in the crowd, sometimes I can't actually see that far ahead. But in this, you're assuming that they can see everyone else, even if you're in a crowd?
That's okay. At this level, yeah, at least I'm not sure I see everybody, but I assume I would do the same if I was at their place at this stage. So this is typically a problem for game theory. It's a game because you have a competition for space here. You are not ghosts, so if you occupy one place, nobody can take it. And you have to optimize for all the agents in parallel and get the desired velocity for all the agents. And we make a hypothesis, exactly. We make many hypotheses, actually. We assume that we will reach a Nash equilibrium, which can be discussed. But it means that it's a situation you are used to, so you can really foresee what the others will do, at least more or less, and adapt to this strategy. So a Nash equilibrium is a set of strategies where nobody can depart without losing something. You have no interest to do something else than what you are doing. But if you have a large crowd with many people, it's just impossible to solve. It's too heavy. So actually what people have proposed is a mean field game. That is, you will replace the precise location of everybody by a density field. So it's like a reduced information that you have on others. This means in practice that the cost that you will optimize will depend on density. So it was introduced by mathematicians, and it became popularized for physicists in particular through a review paper written in particular by Denis Ullmo. That's how Denis Ullmo is in a lab very close to mine. We started to discuss, and from this discussion it came out that mean field games could maybe explain these experiments that I have been showing to you.
So in these games, the players always make the most optimal decision given the situation, right? So everyone behaves in the best way possible.
So yes, they will optimize their cost given that the behavior they expect from the others. Games do not always give the optimum for the global optimum. I don't know if you know Prisoner's Dilemma, for example, where everybody will choose a bad choice. But the idea is at least that you have, we take Nash equilibrium because it's a reference point. We could discuss if people do this and how we go there and so on. But at least it's a well-defined situation. So I will tell you a little more about the formalism. So again, we start with Langevin dynamics. I think you have seen this quite often. So now my desired velocity, where I want to go, is there, but it's perturbed by some noise that could be the perturbations of the others. Of course, you understand that I have no scale separation that allows me to do this in a very controlled way. It's always, in this field, we do things we are not allowed to do, but we do it and we hope it works, more or less. So in this model, you see that at the microscopic model, I have no interaction. I assume just Langevin dynamics, so there is no interaction term. Now, each particle will have a cost, so an individual cost. And so let's take some time to decompose it. So this is not really it was already proposed by mathematicians, this form, in particular to model pedestrians. So there is one penalty, one cost related to the velocity. You don't want to go too fast. Then there is one cost for the density. So that's where the only place where the interaction comes in is here. And okay, for historical reasons, I would say G is negative. So it's a repulsion. So that people want to avoid high density regions. You have a potential. So this is where you will model walls, or in our case, the cylinder. You can put a very high cost, and this prevents people to be in certain places. All this is a running cost integrated over time. And you can have a terminal cost. So for example, for an evacuation, you want to be outside at the end of the process. So this density is where the mean field assumption will come in. We will replace the precise location of other people by some average. So you can think of it as an ensemble average. And the cost itself is also taken with an ensemble average. So then each person wants to minimize this cost. And you have to remember that the value of this minimum cost is called the value function. So we will see it again. Please remember, its notation is u. And so we will choose the desired velocity in order to minimize the cost. So now we have to find some equation for you, and it's based on Bellman's principle of optimality. So the idea is the following. Imagine, okay, I was in x naught at the beginning. I go to xt. On my way, I'm in x prime. Once I am in x prime, in order to continue my way, I can just optimize this part of the path. I don't have to know what happened before. So this is a strong, it seems obvious maybe, but the fact that I don't need to know the past will allow me to write something for my optimization at this time. The only thing that comes from the past is the fact that I'm in X prime. So I arrived in this position. That's the only influence of the past. And in general, I don't know X prime, but I can know it in a specific case when I'm very close to. So I was in a time t0, and just if I'm very close in time, I can infer the new position. So it would be, if I had a deterministic model, it would be just the velocity times dt. Here it's my desired velocity plus some noise. But so once I know X prime, I'm back to again to optimizing for the rest of the time without caring of what happened in the past. So I will skip the slide with the detailed calculation and tell you the result. So based on this reasoning, I can make what is equivalent to a Taylor expansion. So it's a bit, I have noise, so you need to do expansions in the proper way. But in the end, you find an equation for you, a partial differential equation, where you see that there is a Laplacian coming from the noise, and you have this interaction term here. And on the other way, from your Langevin equation, you can derive Fokker-Planck equation or Kolmogorov diffusive equation, depends if you are a physicist or mathematician. And you have also diffusion due to the noise. So you have two coupled equations. So it may not be obvious. Here you see a rho that comes into the equation for you. Here you had the desired velocity. And from the optimization of u in the intermediate steps, you determine that this desired velocity is a gradient of u. So if you replace here, so now you have two coupled equations with two variables. So that's fine. But you can notice that one equation is forward in time, as usual, with the normal plus sign in front of the Laplacian. But the other one has a minus term in front of the Laplacian. So it's an equation backward in time. And you see it also from the boundary condition. For rho, we have the initial condition as usual, but for u, it is the final cost that we know. Because when we take t equals big T, the integral cancels, and so we know that u is only the terminal cost. So it's a bit tricky to solve numerically. You have a structure which can be, so as we were discussing, there are many people studying the numerics in these problems. So there is a change of variable, which is very useful, which is the following. You have this transformation. You don't need to see the details, but it's a Kohlhoff transformation, and it's meant to linearize the equation. So you have two new variables, no matter what it is. But you see that before you had this term gradient square and so on. With the transform, it disappeared. It's still nonlinear. You have some products there, but it's a shape that physicists know very well. It's a nonlinear Schrödinger equation for both variables. And so it makes things easier for solving numerically and so on. Still, you have one forward in time and one backward. So you can solve iteratively, for example. One thing which is very useful with this form is that, you know, I said under walls or under the cylinder, you want to put a very high cost so that people do not come under the walls. But it means your cost can become not infinite, but very high with steep gradients. And numerically, you don't like it. Here, if you put that u is infinite, you will find that phi is 0, and gamma we can show also. So it's much simpler as a boundary condition to have a limit to 0. So that's one reason also why we like this transformation. It's even easier if we are in the stationary state. So for our experiment, we can be in the frame of the cylinder. I just wanted with this slide to stress, usually when we are in stationary state, we just put time derivatives to 0. It's almost true for density and velocity, it's true, but for the value function, it's not true, because you have this integral with time. So actually, it's linear in time. Okay, it's just a detail that you have to take care when you write stationary state. And that's what you find with this model. So you can define some characteristic length and velocity. Some are linked to the cylinder, the radius of the cylinder and its speed. And for the pedestrians, the healing length is how far you will feel the perturbation of an obstacle, for example. And you can also define a typical velocity. So this allows to define adimensionalized ratios and to explore the phase space more efficiently. If you look at these density fields, you find very different things, and you feel that in this quarter, it resembles more our experiment. So we try to optimize the parameters, so as to fit the data. And here is the thing. So we have the game on the left and the experiment on the right. Of course, the experiment is more noisy. But you have the densities on both sides and a void which is symmetric in front and behind. And even more, more interestingly, we do find some lateral displacement. People will avoid the cylinder because they know that even if at short horizon their situation will be worse, they will be crushed like this. On a long time, it's beneficial because it will not last for a long time, and they can avoid the cylinder more efficiently like this. Okay, so this is the first summary of the various approaches I've been showing. So here we have the mean-field game that reproduces the best the experiment. And this was for the case where people face the cylinder. So we assume, even in the theory, we assume they have a full knowledge of what's happening. At least they have a lot of information. So before doing this modeling, when we had done the experiment and discovered this curious reaction of crowds, we contacted some colleagues in Argentina, and they proposed to do again these experiments. So the nice thing is that they found the same thing as we did, with the highest density on the sides, but they could choose other configurations. So they did also the case with random orientation, where only a subset of people see the cylinder arriving. And then they tried also, because there was this thing of anticipation, so they said to people, do not anticipate. But it seemed that when you see the cylinder, people can't prevent from anticipating. So they asked them to show their back to the cylinder, so the cylinder was coming like this, and not to anticipate. And in this case, you can recover the granular case with the highest density in front. And also for the displacement field, you see that you go from lateral displacement. it's still true for the random orientation, but a little more noisy. And for the no anticipation case, you recover the butterfly structure. So this, depending on how you interpret it, you can say it's various degrees of information or various degrees of anticipation. You don't anticipate so much. So how can we put this in the model? Something which is quite classical is to put a discount factor. So the only difference with the previous case is this exponential in red. So you say that the anticipation is very high when you are close in time, but as you are further in time, you will not take it into account for your optimization of the cost. And so it changes only in the equation for u. It will add a gamma u. Okay, it seems quite a minor change. And so for gamma equals 0, we recover the previous case. So again, we can study the phase space. Okay, I will just show you for two cases where we can estimate some typical length, a length which would be based on the reaction of the pedestrians, the distance at which they should start to move to avoid the impact. And I made a mistake because there was something written under it. It's how much the cylinder has advanced during the same time, basically. And you see that if you are in this case, pedestrians have time to avoid the cylinder, and in the other case, they cannot avoid the cylinder, and they form this granular-like structure. So we can understand a little these things. Okay, in this case, with this gamma, the discount factor, there are numerical issues because this transformation that I said was very useful with the Kohlhoff transformation. It makes appear now some log, phi log phi. And I didn't put the gamma equation, but it's even worse. You have several logs arriving. So it's a bit tricky to deal with the boundaries. You still want to do this to avoid the infinite values of u at the boundary. But what we did is having, so here it's the discretization of the equations. You have the cylinder here. And in the first region, we will still do this transform, but we will estimate that the effect of this term is negligible in front of the other one. And in the remaining, we will keep the u row variables to avoid, now it's useless to go in these transformed equations. So it's just a way to say that there are many numerical issues behind these models. So this you have seen already in the case of pedestrian facing the cylinder. Now if I put gamma equals 1/2, so it would mean a typical time 2 seconds for the anticipation. Now I start to have a less pronounced void in front of the cylinder, and I start to have some component of the displacement that go away from the cylinder. And now if I am in the case where I suppress the anticipation in the experiment, I recover so density in the top, and I can also have it in the model by choosing a larger gamma, so meaning a smaller, here you anticipate very little, it's less than a second. And you find also in the model this butterfly shape, So it means that you have a model where by just changing one parameter, you can have the whole span of behaviors between the crowd one and the granular one. Now we could also consider other cases. So this is another example. We assume we are in the subway. And you know, when there is a strike, sometimes you have so many people on the platform that not everybody can get into the subway. So here we don't see the... OK, so at first on top you have the platform. And then the subway arrives, the metro arrives, so people go into the subway. But you see that at one point, people realize that they will not be able to go into the subway. And so they decide, you see now this light region appearing, they decide not to go. So this is another kind of anticipation. It's not full yet, but people anticipate. So it's the same model.
That's data?
No, that's simulation. Yes. And just the photograph is to make you feel that it's very realistic, but you can believe whatever you want.
So is there just a terminal cost of getting stuck at the door? Or, is that
we didn't put it, but yeah, we could think about it. So now more about the future, what is missing in these models. Bertrand was already, this is from his team actually. He was already mentioning that these fluid models, they are too much able to squeeze into any hole. So here they had a model, a granular model, and what is supposed to be the equivalent macroscopic model. And you see at the beginning the voids are at the same place, it matches quite well. But at the end, the fluid goes faster than the granular one. And so there is an issue about taking into account granular characteristics. So we have a challenge to be able to put the fact that the pedestrians are discrete. So we could for the improvements, maybe I can mention first. So we could easily put several pedestrian times. Actually, some people did some models with not compared to experiments, but from the numerical point of view with lane formation and this kind of things. So in the cost, I had this term. Yeah. So I could take into account some more refined effect of density. So I could, instead of linear, I could put another form here. But I could also what is usually called congestion effect, and there are some people who explored already this a little, but it's difficult when you do it, is adding some term here that will tell that you have a higher cost to go fast when you are in a high density region, because it's more difficult to move. And the last place where we could put more things about interactions and the effect of density is in the microscopic model. You have seen that here it's based on Langevin, so it means no interaction at the microscopic level. And this could maybe be included. So we have a thesis starting and some collaboration with mathematicians on this to explore this. And OK, I think that's my last slide. Thank you.
Is time for question?
Yes.
So in the mean field model where you had like the infinite time horizon, it seemed like the density deformation had some symmetries. Can anything interesting be said about that? And can it be connected to questions of like dissipative versus dissipationless dynamics, and maybe like fluid versus solid, or fluid versus like viscous versus elastic mechanics? It's kind of I haven't fully.
Yes. there are some symmetries, you're right. I don't know how to phrase it directly in the terms you suggest, but in the structure of the calculations, there are some similarities with many other formalisms. For example, here, why do they have put a minus? Because you can say that this is Lagrangian L minus V and write it as we do for mechanics. Or there are some similarities with the formalism also of large deviations. And so, yeah, we would like to understand better what is hidden behind. But
does like the global optimization result in any like new like conserved quantities?
Sorry, I don't hear you.
Are there any like new conserved quantities that emerge, maybe?
That would be hidden in the formalism.
Like, is the deformation, does it like return to its initial state, for example?
Yeah, I must escape from the...
Sorry. Does the crowd return to its initial state, or is there like...
It takes a very long time here, so we could put, it depends on what you put as a terminal cost or whatever. Here we have no string force that would take people back in the wake, so it's more, yeah, very far. It will, you will have uniform density, but it takes quite a long time. Yeah.
Because it almost looks like this like Stokes flow where you can reverse time and reverse the flow.
Yeah, yeah, it looks like this. Yes. I don't know how we see it also in the experiment, but how to phrase it in terms. These are interesting ideas that you mentioned, but yeah.
Is it possible to perform something optimal control in your framework? So instead of consider how the crowd exit the space, you ask how to control the crowd.
Oh, so you have two different questions. So there are families of models where you will use a more sophisticated microscopic model, and from time to time you do optimal control based on the current state of your system, and then it updates the desired velocities and you continue. So that's one way to do it. Now, you can have one thing I would like to explore is also the role of information that people have, because this is one question we had with people dealing with safety in big events. It's where should we put the people giving information or helping or and so on. And okay, these are things, so it's controlled by information, you could say. And after that, what was your, I'm not sure, it's enough. Okay.
My question actually kind of relates to the role of information, but also the role of the information that an agent would have. Mm-hmm. So in this case of evacuating, say, a burning building and there's two doors, it may be optimal to go through the one that no one's at, but if everyone's going through that one door and no one's going through that door, I probably think that there's a reason, and I assume that I don't have all the information and I behave. I'm kind of like, my strategy is going to be sticky. I'm going to look for what other people are doing. Is there, a simple way to implement these kind of higher order reasoning into that mean field game side of things?
Yeah, this would be almost the opposite effect, like herding effect, that you would like to follow the others. Yes, and you have studies trying to see in case of emergency, for example, how you have new social organization with some people who spontaneously become leaders because they seem to know what to do, and others who are following and so on. So in this frame, we have to think how to, because you cannot put a plus and a minus for the same row term, but some people use this with the opposite sign for the density. It's possible also.
So I guess on the macroscopic description, it would be difficult to implement.
well, if you just assume that everybody wants to do as the other ones, you will often it gives some instability where you have or you have to find a way to bound the density. But it's interesting, these things, when you have at least two types of people or yes.
So if there are no more questions, I think it's time to stop. Thank you.